We are now going to begin our foray into exponential functions, and we'll start this whole meander, I guess you could call it, with just the basic concepts of what an exponential function is. And in fact, I'm going to more focus on exponential equations here and word problems and applications, because that's really the best way to learn about exponentials. In my opinion, exponential and logarithmic functions tend to be the most important that we'll experience in an algebra course, mainly because a lot of things are modeled using exponentials. There are a few prerequisites here. We're going to be building a few tables. You'll have to know how to work with exponents, and you'll have to know how to graph by plotting points, just because I'm going to do a couple examples involving that. Now, there are other prerequisites, but they all pretty much involve just problem-solving skills. Now, our very first example here, and normally I wouldn't start with an example, I'd actually start with a concept, but I want to build the concept from an example. And this involves a video clip from the Lucy Ball show, or actually the Lucy show. Here we go. I want you to listen to this just for a moment.
Just listen. If you put 1 penny in the bank today, 2 pennies the next day, then 4 the following day, and keep doubling the amount each day, you would have enough money to buy your furniture in 19 days.
You're kidding. You mean if I doubled a penny 19 times, I'd have $1,500?
You would have more than $1,500. Now, you just think about that.
Okay, so let's actually think about that. So that problem is essentially saying, suppose a penny is put aside today, invested or put into the bank, and it doubles in value each day. I mean, in that problem, actually, he's saying you put a penny aside today, you put 2 pennies aside tomorrow, you put 4 pennies aside the next day. So he's kind of forcing her to put her money down each day. But I'm saying, suppose you could just drop a penny and somebody who's willing to double it every day. Let's build a table for the amount we would have after 1 week. So what I'm going to do is use function notation here. I'll let D equal the number of days that have passed, and I'll let P be the number of pennies we have at that number of days. So on the 0th day, in other words, the initial day, and that's generally what we start with when we're talking about doing something today. We talk about the 0th day. We have 1 penny, but tomorrow it's going to double, right? Tomorrow, the beginning of day 1 day ahead now, we're going to have double that, or 2 pennies. And the next day, we're going to have double that too, or 4 pennies. Now, how did I get that 4? Well, let's see. Let's go back and see how I got the 2. The 2 I got from saying, well, I'm going to double what that last number was, which was 1. This 4 I got because I'm doubling what that last number was, which was 2. The 3rd day, I'm going to double the last day. Well, let's see here. The last day, I'm going to double what the last day was. The last day was 4. Oh, but wait, let me write this as 2 times 4 is just 2 times 2. So that's 2 times 2 times 2. Now you might be asking why I would write it like that. I'll show you in a moment. But it's just double 4, which is 8. 4 days later, we're going to double up on that 8. And everybody knows that double up of 8 is 16. But let's see how we would have done that mathematically. We would have doubled up on that 8. But again, 8 is just 2 times 2 times 2. So that'd be 2 times 2 times 2 times 2. Well, this gets kind of long-winded writing it out like this. So let me use exponential notation. That's 2 to the 4th power. And this one back here was 2 to the, actually let me even write this with a red 4 there. This is 2 to the 3rd power. And this is just 2 to the 2nd power. Right? And actually, this one right here is 2 to the 1st power. Right? 2 is just 2 to the 1st power. And you think, well, geez, there's a pattern going on, right? On day 1, we have 2 to the 1st pennies. Day 2, we have 2 to the 2nd pennies. Day 3, we have 2 to the 3rd pennies. Day 4, we have 2 to the 4th pennies. But some people would argue that day 1, or day 0, I'm sorry, doesn't work out. But it actually does. Because remember, 2 to the 0th is equal to 1. Any number to the 0th power, as long as it's non-zero. is equal to 1. So that must mean that 5 days later, we'll have 2 to the 5th pennies. Just following the pattern that we've just started to develop. 2 to the 5th is 32, which does work out, so I'll just write that in. 6 days and 7 days later, I know you might not be able to see the 7, it might be off your screen, but 6 days later we have 64, 7 days later we have 128. And by the way, 64 is 2 to the 6th, and 128, if I can catch up to myself, is 2 to the 7th. So this is an interesting situation. Turns out that our outputs depend on an exponent, the value of an exponent. And this gives us an idea for a new kind of function, one that's called an exponential function. Now, before I get into really the guts of an exponential function, let's plot these points back here, these ones that we've listed out. These ordered pairs can be listed as 0, 1, 1, 2, 2, 4, and so on and so forth, right? So I'm not going to write them all out, but you get the idea. Dot, dot, dot. So let's go ahead and plot those points. And I'll use a pretty decent color here to do this. Let me change colors. So 0, 1 was our first one, so I'm going to plot that right here. And then 1, 2, it's right there. 2, 4, so 1, 2, 3, 4, right there. Let's see, so 3, 8, that's 4, 5, 6, 7, 8. We can already see it's not a line, right? Let's see, so it's 1, 2, 3, 4, 16, so let's see, that's 8, 9, 10, 11, 12, 13, 14, 15, 16. You can see what's happening. It's really climbing up there. And then I'll see if I could do 5, 32 on here. And there we have it. In fact, let me label these. And then I'll connect them up with a nice smooth curve. And this smooth curve, if you notice, it's increasing faster and faster as time goes on. And that's a very good characteristic, a very good way to know that you're dealing with an exponential function is that it grows, well, exponentially. That's why they call them exponential functions. It's a basic look of one. Now, we're missing part of the graph, actually. This graph, to be very honest with you, continues on this way as well, but we'll talk about that more in a different lecture. So I just want to get the basic idea of what the kind of the overall look of it is as time goes on, as it ticks on and on and on. Now here comes the meat and potatoes of this problem. We want to write a function that represents the situation. Now, here is our table of values, and you can kind of tell that the pattern is whatever we plug in for d, the output will be 2 to that power. So, if I plug in to our function 1, the output will be 2 to the first power. If I plug in 2, the output will be 2 to the second power. If I plug in 15, let's say, then the output should be 2 to the 15th power. Now, if I plug in a variable, like the number of days that have passed, the output should be 2 to the, well, follow the pattern here, the d power. So it turns out that our function is just p of d, number of pennies at day d, is equal to 2 to the d power. Now remember in that problem, that the video from the Lucy show there, he said that after 19 days, Lucy would have enough money to buy her couch. And she was pretty impressed with that. Well, let's see actually how much somebody would have, let's say, after a month. And in this scenario, let's consider that to be 30 days. It doesn't really matter. You could say 31 days if you want. You'll just have more money. So this means that P is going to be evaluated at 30. We're going to let D equal 30. So this is the amount of pennies we're going to have, 2 to the 30th. Well, you might not feel as though that's a lot, but if you bring up a calculator and just type in 2 raised to the 30th power, you'll find out very quickly that that is quite a bit. of pennies. Remember, this is pennies. So this is going to be 10737. Was it 41824? 41824. Now that's in pennies. I'm going to put a decimal point here to make it dollars. So let me put a comma and a comma. Oh, that's just $10 million. Almost $11 million. Starting from a penny, doubling every day. For a month, just 30 days. That's pretty ridiculous, but if you think about what this graph shows, it shows that the amount of money we have grows continually. After 5 days, it's shot up this much, all the way up to here, and it's just going to grow faster and faster as time goes on. So this is the behavior of what's called, well, this is called exponential behavior. The official definition of an exponential function goes like this. The function p of t. Now, it's very important to realize here that there's only one, well, there are two unknowns, but there's one independent variable and one dependent variable. The independent variable is what we're plugging in, right? So we're plugging in t. Notice where that independent variable is in this equation. It's in an exponent. That's a great indicator that you're dealing with an exponential function, is that your unknown is in the exponent. That's the only time you call something an exponential function, is when your unknown is in the exponent. Okay. So this function, p of t, equals p naught, let's pronounce p naught or p sub 0. I'll just write this in as p, quote unquote, p naught. P naught times b to the t power, where p naught is called the initial population and b is called the growth or the decay factor. This is called an exponential function. Now a few of these things need descriptions before I go any further. One thing is that you notice is in parentheses there I have that b cannot equal 1. The reason why b cannot equal 1, well, if it did, you'd have something like this. Let's just make a exponential function up. Let's say we just had some initial population, let's say 2, and let's say our base was 1. Well, then 1 to the power is just still 1, so this is the same thing as just saying 2 times 1, or in other words 2. This doesn't grow. This is just p of t equals 2. There's nothing changing with this. It doesn't matter what I plug in for t, this is always going to be 2. So that's a little bit silly. You can't, we kind of say that you can't let b equal 1 because, well, that's not exponential. It's not doing anything. The other condition, that b has to be positive, is sort of a tricky condition. I'll tell you why it's true, though. Let's suppose for a second that we allow b to be negative. Okay, so let's just say we have the same initial population, but we choose our base for our exponential part to be negative. Well, that's fine if p is like 5, right? If p is 5, then you have 2 times negative 1 to the 5th power, which is going to be 2 times, well, negative 1 to the 5th power is just a negative 1, which is going to be a negative 2 altogether. The issue happens when you do like things like p of 1/2. That would be 2 times negative 1 to the 1/2 power, and remember 1/2 is a square root, so that's 2 times the square root of negative 1, and we've got an issue, right? That right there tells us that we can't go any further. Cross that out. That's non-real. So that's why we kind of require that b be positive. And again, the first reason was why we require b to not equal 1. Now let's explain the other thing here. P naught is called the initial population. I'd like you to really know why it's called the initial population. It's very easy to understand why it's called the initial population if you take it mathematically. If you let t equal 0, t is just time. It stands for days, weeks, years, hours, seconds, whatever it is. If you let t equal 0, in other words, time 0, right now, the initial time, let's see what this turns into. It turns into p naught b to the 0th power. But b to the 0th, any number to the 0th power, as long as that number is non-zero, is going to be 1. So that's just the same thing as p naught times 1. Well, p naught times 1 is still just p naught. So notice that p of 0 is equal to p naught. In other words, p naught is the value of the function at time 0. That's why I call it the initial population. So we now have seen why this is called the initial population. B, being called the growth or decay factor, that actually determines how quickly things are growing or decaying. So if we go back to our example we had a few moments ago, this one right here with the Lucy Ball show, notice that the base for our function, in fact, let me go to the function itself, the base for our function is 2. It's because it's doubling every day. So that tells us, I mean, when I read that, p of d is equal to 2 to the d power, I immediately think, oh, the base of the exponent is 2, that means it's doubling. If the base of the exponent was 3, it means it would be tripling. If the base of the exponent was 4, it mean it'd be quadrupling, and so on and so forth. It's a very nice kind of organic way to feel that out. By the way, this is in exponential function format, but if you really want to match this function here up with our definition, then we need to put the initial population down. Well, if you read the problem, and that's, by the way, I used the letter P not because of pennies, even though I said it was for the fact that we were dealing with pennies. I use the letter P because P I always use with population models, and I consider an amount of money in my bank a population of money in my bank. Anyway, this can be written in that form of P naught times b to the t power. If you think about the initial population, initially we had 1 penny, and then it doubled every day. There you go. That's the same thing. So, but often we don't write the 1, so this would just be p of d is equal to 2 to the d power. Now, I don't expect you to be an expert right now, but at least you can kind of understand the bits and pieces of this. I'll refer to a lot of these as we go along. There's more to the growth and decay factors than what I'm saying right now, but we'll get into that in a moment. I don't want to, or actually in a future lecture, I don't want to over confuse you right now. Just know that whatever this value of b is, whatever that value of b is, it controls how quickly things are growing or how quickly they're decaying. And notice I haven't given you a decay example because they're a little more involved, I guess is a good word for it. They're a little more involved, and I don't want to get too involved at this point. Now I want to give you another kind of visual of exponential growth here. This is a lily pond example from Wolfram Demonstrations Project. And what I'm going to do is control the number of days that have passed, and let me describe the situation. You have a water hyacinth. A water hyacinth is just basically a water, like a grass. It's not really a grass, but it's a type of weed that's in water, and it doubles in population every 12 days. So every 12 days, if you started with 1, 12 days later you'll have 2, and 12 days after that it'll double that 2 and become 4, and 12 days after that it doubles and becomes 8, right? And so on and so forth. So what I want to do is show you, this is a big pond of water. There's a little green dot in the center. That's one water hyacinth right there. And I'm going to let time go on. So it's Thursday, November 10th, 2011. I'm going to see how long it takes to fill up this pond. So here we go. I'm just going to hit play on this. And now notice the days are just jamming forward. I'll slow them down a little bit. See, we're into December, January. You don't see a lot of, I mean, it doesn't look like it's changing, but it's actually been doubling. It's just very slow. You'll see this point get bigger and bigger. Actually, it stopped, so hold on. Okay, so we're back to moving forward. And you see now that the dot is actually doing something in here. Okay, we pause again for a moment. And I just want to point out that this dot's a little bit bigger because it's been doubling. I mean, there might not be a lot of water hyacinth here. We're at day 178 right now. But as we move forward, you'll see it does actually, once you start getting just a little heavier population, doubling really makes a difference. So let's go ahead and continue forward. You can see that it's growing and growing, right? Now you can really see the doubling. We're at 250 days. I mean, the population is basically exploding. So it took a very long time initially, but then once you get some growth going on there, let me pause it right now. 357 days. Once the growth starts going, it just booms, and that's generally how exponential functions work. Is that it may seem slow at first, but after a few steps, it just starts blowing up. And I really like this example actually. So let me use this example with our money example. So I'm going to kind of mix the two. So let's suppose our penny doesn't double every day, but now doubles every 12 days. So just like that water hyacinth example. We're going to build a table representing the first 60 days of return. Now, I'm not going to build a long table with 60 days in it. I'm going to take them 12 days at a time. So I'll have the number of days that passed here. That'll be our input. That's what we get to control. We get to control how many days pass. And depending upon that number of days that have passed, we'll have a certain number of pennies. So this is going to be a new function. I'll still use the letter P for it just because that's a letter I commonly use for functions. And I'll just worry about day 0, the initial day. Then I'll worry about 12 days later, and then 12 days after that, and another 12 days after that, another 12 days after that, and finally another 12 days after that. So that's the first 60 days divided up into segments of 12. Initially, I only have 1 penny, right? So that would be our 2 to the 0th. And then day 12, it doubles. So I'll have 2 pennies. And this is what's weird, is that this is not 2 to the 12th, is it? It's 2 to the 1st. So what the heck happened? Well, we'll find out. 12 days later, it doubles to become 4, which is 2 to the 4th. Or 2 to the 2nd, sorry. I didn't mean to say 2 to the 4th. And then 12 days later, doubles again and becomes 8, which is 2 to the 3rd. And so on and so forth. But what's really important to ask is what happens, what if I don't want to know how much money I have at exactly a multiple of 12 days? What if I want to know how much money I have after 13 days, or 15 days, or 21 days, or 37 days? In that case, you're going to have to really kind of just take a pattern from the beginning here, try to develop some way of talking about these powers for the first 12 days first, so you can kind of see what's going on. Well, if we were at day 1, so let me just put up a side table here. If we were at day 1, I know that I would have more than a penny. Well, okay, you can't, if you have more than a penny, you have to have at least 2, but let's just say they give me fractions of pennies. I know I have more than a penny because it's growing. And yesterday I had 1 penny, so I should have a little bit more. But it should be less than 2 pennies because that doesn't happen until I hit 12 days. It's going to be a fractional part of that. So here's the fractional part of it. 2 to the 1/12. Now, the base of 2 should make sense. Everything's based on doubling, doubling, doubling. So the base of 2 should make sense. But why did I choose 1/12? Well, it takes 12 days total to make the double. Right? So in other words, when day 12 comes along, I'll have 2 to the 12 over 12. But wait, 12 over 12 is 1. And look, that does match. It does match that right there. Well, let's see if this fractional exponent will work for 24 then. 2 to the 24 over 12, that would be 2 to the 2nd power, which is 4, which is exactly what we get. So this actually will work. Essentially, what I'm saying is, if it doubles or triples or quadruples every 12 days, then you'll have that base for doubling or tripling or quadrupling, 2, 3, or 4, raised to the something over 12 power. And that something is just the number of days that passed. In fact, if you continue this on, you could do like, well, after 101 days, how much do I have? Well, you'll have 2 to the 101 over 12 power, whatever that may be. And after d number of days, you'll have 2 to the d over 12 power worth of pennies. And this actually tells us the function here. So just as not a lot of textbooks have this, suppose things double every so many days, but the fact is that's a very important skill to have. So let's go ahead and build a function for this. And just using the pattern from the table, actually, we've already written it. P of D, the population of money that I have, depending upon the number of days that have gone by, is equal to the initial population. Maybe I should write out, it's equal to that formula, right? Oops, there should be a D here, not a T. Right. So I'll just insert what I know. Initially, my population is just 1 penny times. My growth factor is it's doubling, sort of. And then it's going to be every d over 12. In other words, every 12 days. So let me clean this up. It's P of d is equal to 2 raised to the d over 12 power. Now there is something very interesting I should mention, or important that I should mention here. Remember that in our initial definition, actually I could just go back to it. In our initial definition here, we had this P naught times B to the T, and we said that B, which is highlighted, is called the growth factor or the growth or the decay factor. And notice the power on that is a T, not a T over something, but a T, or a variable. So if you want to find out what the growth factor on this function really is, it's not 2. The growth factor is kind of a manipulated version of 2. If you look at this, this is the same thing as saying something to the d power, and that something is 2 to the 1/12. Remember, that's from our talk from a while ago about exponentials. If you forgot that, please go back and watch one of my videos on exponentials, exponential notation, and that type of stuff, powers and radicals and rational exponents. Because this is a law of exponents that you can break that apart. Powers to powers multiply. So now I have it in the form of P of D is equal to something raised to the power D. And that something is actually our growth factor. So this is called the growth factor. It's our first time, of course, with most exponential objects, but even people who've dealt with other classes who have taken intermediate algebra in the past probably haven't seen this. This is not something that a lot of intermediate algebra textbooks go through, but I think it's very important for you to know it. So just know that if you want to find the growth factor for an exponential function, make sure that you write the base raised to the only the variable power, not the variable over something, but basically factor out. Do this business, right? From here to here. So that'll give you the growth factor. Now I can't leave this alone. I have to ask one more question. I always, with exponential functions, I always do. So how much would you have after a year? How much after a year? And remember, we had like $10 million after 30 days if it was doubling each day. But we're not doubling each day, we're doubling every 12 days. So let's see how much we have after a year, and let's just say that's 365 days. I know there's leap years and stuff like that. So 365 days, we'll plug that in, 365. So we want to find out what the population of pennies is after 365 days. Well, that'll be 2 to the 1/12 raised to the 365. Now, at this point, there's a couple things you might want to try, but I know it's not going to work in this case. But at this point, I would probably try to do this. I'd multiply these two powers, so I'd have 2 raised to the 365 over 12, and see if that reduces. But it doesn't. I mean, it only reduces slightly. So it's better to just grab a calculator. So I'll just go ahead and open up my calculator here, and I will type in 2 raised to the, start a parenthesis when you have an exponent like this, when you have some math in an exponent, 365 over 12, and end your parenthesis, even though it's not necessary. and you'll have this many pennies. Well, we'll see how that compares. So this is equal to 143327. What do we got? 3380. And again, I'll convert from pennies to dollars here, put in some commas. Oh, we actually have more money. Well, of course, we had it going for much longer. But $14 million. Not bad. More money, but it took us 365 days to do it. Okay, and it's more money because it was going every 12 days, but again, for 365 days. Finally, I just want to draw your attention to something. And again, this is not something that most textbooks talk about. Your textbook probably doesn't have it. I know my textbook doesn't. But I want to compare two objects in mathematics that you have been introduced to, one being linear functions and one being this, exponential functions. And I want to compare them and tell you that they're actually very similar to each other. So I have a linear function right here. I'll just write that in, linear. mx plus b. That's basically y equals mx plus b right there. And this is an exponential function. And it's exponential because the unknown is in the exponent. It has an initial population and a base, right? There we go. But these are very similar, sort of. If you take a look at, just give a simple example like this. Let's do y is equal to 3x plus 1. And we build a table. You have x's and y's, and you can choose whatever you want for x's really. 0, 1, and 2. And let's plug in negative 2 into x here. That's negative 6 plus 1. That's a negative 5. Plug in a negative 1 for x. You'll get a negative 3 plus 1, which is negative 2. Plug in 0 for x. You'll get a 1. Plug in 1 for x. You'll get a 4. Plug in a 2 for x. You'll get 7. Something you should know, you should recognize at this point, being as advanced as you are, that each step by 1, each of these x values are stepping by 1, right? Notice what the y values are changing by each time. To get from negative 5 to negative 2, it's adding 3. To get from negative 2 to positive 1, it's adding another 3. To get from 1 to 4, it's adding another 3. To get from 4 to 7, it's adding another 3. So there's something, this is called the slope addition property. Let me write that down. Slope, oops, that's not how you spell slope. And it basically means that if you increase x by 1, so you add 1 to x, it'll increase the y value by m. It'll increase the y value by the slope. So you are adding the slope. That's why I call the slope addition property. Now let's take a similar example for the exponential function. So let's suppose that we have an exponential function. It looks like this. Y is equal to, I should use same colors. Y equals 2 times 3 to the x. Let's build a table here. Notice, let's start talking exponentially here. The initial value is 2. In other words, our initial population is 2. So we have 2 objects. And that 3 is the growth factor. It means it's tripling. So I start with, let's say, 2 cars and I triple every day. Or I start with 2 rabbits and the population triples every week or something like that. Okay, so that's whenever I see an exponential function, I immediately put some situation to it that makes sense to me. The rabbit one actually does kind of make sense. Well, no, not really. All right, so let's plug in the same values for x here: negative 2, negative 1, 0, 1, and 2. When x is a negative 2, we have 2 times 3 to the negative 2 power, which is actually going to be 2 over 3 squared, right? You can rip the negative off and pop that downstairs. And that's 2/9. So let me write that in there, 2 over 9. When x is a negative 1, you have 2 times 3 to the negative 1. Remember, you can rip the negative off the exponent, and that base of 3 will drop downstairs, and the exponent will become positive. So that's just 2/3. When you let x equal 0, well, that's the initial value. And 3 to the 0th is just 1. So it's going to be 2 here. And I could have told you that just by reading the initial part here, right? Same thing actually over with the linear function over here. X equals 0 is the initial value. It's the y-intercept. So that's my initial value there, but p naught is the initial value for an exponential function. All right. Let's see. Plugging in x equals 1, we'll get 2 times 3 to the first, which is just 6. And finally, plugging in 2. 2 times 3 to the second power, we'll get 2 times 9, or 18. Now, I told you that linear and exponential functions share something in common, or something similar in common. Notice when I built this table, on the left-hand side for my inputs, I was stepping by 1. I was just increasing the x values by 1 here. You can continue building the table if you want. And something happened with the outputs. Each of these outputs, did they increase by the same amount every single time? Did we add, like, to get from 2 to 6, we added 4, but to get from 6 to 18, that's not adding 4. So it's not an addition problem. But notice that to get from 6 to 18, you would multiply by 3. To get from 2 to 6, you would multiply by 3. To actually get from 2/3 to 2, you would multiply 2/3 by 3. To get from 2/9 to 2/3, you would multiply by 3. Now notice how similar these table setups are. This idea that every step in the x direction you multiply the output, the y value, by the base is called the base multiplier property. Which basically means every time you add 1 to your x value, your y value gets multiplied by the base. That's a base multiplier property. Now, again, this is supposed to be, it didn't really work out that way, it was supposed to be the conceptual lecture behind what is the idea of an exponential, but I want you to know that I'm going to repeat a lot of this stuff, not definitions. I'm not going to sit there and say, oh, remember, or, well, I will say remember, but I won't rebuild the definitions. I'll just say, remember, this is the base multiplier property, or remember the definition for this is, but I'm not going to redefine anything. So this is very important that you watch this entire lecture. The next lecture I'll focus on actually doing applications with these and building exponential functions from applications.